Okay. Good morning, everyone. Let's start. Do you have any questions before we start? All right. So let's begin where we left off last time. So last time we were playing around with the understanding of critical region. So again, right, we have a test, we have a hypothesis, H0 and H1, whatever they are. We have the critical region. I mean, actually, let's just go with an example, right? That makes it easier. So we have x1, xn, IID, normal, unknown mean, variance 1, and the known is the unknown mean is 0. The alternative is mu is equal to 1. So first, we mentioned that both of these are simple hypotheses. Simple hypotheses are convenient because they allow us to compute, right? So, okay, so we have some critical region, right? And let's say our first one is x bar bigger than k, for example. This doesn't have to be the only critical region we can use, but suppose that this is, one of the critical region that we go with, then type 1 error is a probability. So, and by the way, right, of course, critical region means that if, right, this happens, right, if we reject, right, the null if C1 happens. That's the whole purpose of critical region. It allows us to accept or reject the null hypothesis. So type 1 error, of course, happens when we reject, but the null is true. Type 2 error happens if the alternative is true, but we accept the null, right? If we do not reject, okay? And so the simple hypothesis allows us to compute alpha 1 and beta 1 completely, right? So if we say if the null happens, we know, so the distribution, the population distribution is completely specified under the simple hypothesis. If we were to use composite hypothesis, for example, that the alternative mu is not equal to 0, right? This is composite. Then beta 1, right? Then beta 1, which is still this, cannot be computed, right? Because, I mean, cannot be computed because alpha, right? Because mu is not completely specified. I mean, how to say this, right? Let's say this expression cannot be computed because, right, the distribution, the population distribution is not completely specified. So that's something we want to keep in mind about the composite hypothesis. This doesn't mean, though, right, that we cannot do anything about composite hypothesis. For example, if somehow we have more information, for example, if we know, right, if we know, on the other hand, I mean, computing this okay? Computing this, because our alternative is mu is not equal to 0. So this is still part of the alternative hypothesis, right? So suppose that for some reason that we know exactly that mu equals to 1, then this is under the alternative hypothesis, then this is still beta, right? This is still type 2 error, can be computed. If we know exactly, if we know more information about mu. All right, so I'm just talking about like different ways that we can form this statement. So in the abstract, the statement of beta, right, the definition of type 2 error just says that is the probability that we do not reject under the alternative. But there are many ways, right, the alternative can happen. If you just say that mu is not equal to 0, then you cannot compute this statement completely, because it's not, the distribution is not completely specified. But if you specify it for some extra reason, all right, and this can happen, then you can still discuss this type 2 error, for example. Anyway, like a technical remark that may affect us later. So, but anyway, right, the point is that we were playing around with understanding, right, how to calculate alpha and beta and with different rejection regions. So don't forget, right, that our overall goal, the overall philosophy, or I don't know, flavor or whatever, convention of hypothesis testing is to restrict, right, is to restrict alpha to a tolerance level, to a small tolerance level, and minimize beta. And this has to do with, our philosophy that we do not, because the null hypothesis is our default hypothesis. We do not want to, we want to give emphasis to the null. In other words, we don't want to go with the alternative unless there's overwhelming evidence that that is the case. All right. So I just want to kind of, remark on the fact that this is due to convention. There's no reason mathematically for us to not do the reverse, which is to fix beta to a minimum level, to a small level, and then minimize alpha. Okay, so we can restrict type 2 error to a small level and then minimize alpha. I mean, mathematically, there's no reason why we cannot do one thing on the other. But this whole convention has to do with how we phrase the null and the alternative. For example, right, the null is like a person is innocent, and the alternative is the person is guilty, right? That's conventionally how we phrase the null and the alternative. That's the default, the person is innocent. So the jury system, right, is such that we do not convict a person wrongly, right? We do not want to say that someone is guilty unless there is overwhelming evidence that that is the case. On the other hand, right, because we give emphasis to the null, we are willing, right, to let some guilty person go free more often than we care to, right? So what I mean is that usually, right, and this is not a precise statement, but usually alpha is 0.05, for example. This we can control, right? We control alpha 0.01, but beta should be about 0.40, for example. Again, it depends on the setup, the hypothesis, but beta, right, cannot be as small as alpha. Beta usually is about 20, 30%, whatever. So again, right, having beta a little bit large means that we're willing to commit type 2 error more often than type 1 error. And again, right, that has to do with how like our culture setup. Another example would be testing treatment, right? We do not want to say that a treatment is effective unless there's overwhelming evidence that that is the case. On the other hand, right, the implication is that we're willing to say that some treatment that it may be effective, but we're willing to say that it's not effective. Right? We're willing to make that error more often. We do not want to make the error that to say that some treatment that's not effective as effective, like very often. Okay. So this is the reason, again, I want to emphasize this is because you will see that a lot of hypothesis testing that we will be doing is driven by this convention. In other words, the way we construct our rejection region, the way we construct our test stat will be driven by this convention. So if you're not aware of this convention, certain things might seem strange that you have no idea why that's the case, for example. All right, so that was a recap of what we did last time. Any question on this? So as kind of last time as well, we were mentioning that we want to look at the code. So let's look at the simulation real quick, okay? To give a context on like the hypothesis test. So here I have the sample size to be 9. I sample from a normal population with mean 0, okay? And I set alpha, right? I set my type 1 error to be 0.05. And so what happens, right? So I just state the null and the alternative here for you. So here the null is true because the true mean is 0, so it's true. And what I would do is I would sample again and again 10 times, okay? I would draw 10 samples with size 9. Each time I would apply the hypothesis test on the criterion, the rejection criterion on these samples. And the rejection criterion is driven by the so-called t-test, right? And some of you might have known this. So this is the test statistics, x bar minus mu naught divided by square root of s squared over n. And this is exactly, the pivot, right, stat for the confidence interval. And in fact, there are a lot of connections between hypothesis test and confidence interval, okay? We'll try to mention that as we go along. But anyway, for now, let's just take this as a test statistic. And we will reject the null hypothesis if the test statistics is large enough. How large is large enough? Based on the alpha, right, criterion, is large enough if it's bigger than the t percentile. So this is t alpha over 2 right here. But because, in Python, this is the CDF. So t alpha over 2 in our notation would be the CDF that is 1 minus alpha over 2 to the left. So that's why this notation, this code, okay? So I would just sample 10 times, apply this criterion, and anytime, right, I reject wrongly, then I will just note that type 1 error has been committed. So this right here is studying type 1 error. So let's see what happens. So for this run, right, all 10 samples do not reject the null because, right, the null is true. So this is correct. These are correct conclusions. So no type 1 error has been committed. But of course, right, this is just out of like 10 samples. The whole point is our sample is random. So let's run again to see if no type 1 error committed. No type 1 error committed again. Right here, for example, right, 2 type 1 errors have been committed. Again, these things are random, right? So alpha equals to 0.05. So out of 100 samples, right, we expect that 5 of them are rejected wrongly. But here, like 10 samples, so it's hard to say. But so pay attention to just how, like the type 1 error sometimes appears, sometimes not, and at different samples, for example, here. Here, I repeat the same kind of simulation, except that now I study type 2 error, right? So to study type 2 error, I must go to the case where the alternative is true. Right? So I still keep the null and the alternative set up this way. Because of this setup, my test stat and my rejection criterion is still the same. Okay, we haven't talked about this yet, but again, for those of you who are familiar with the t-test, this is the same thing. And again, right, the t-test is driven purely right by the setup of the null and alternative. And this is why I said that the convention that we want to give priority to alpha, right, gives rise to the t-test construction this way. Notice the t-test only deals with alpha, right? It's only influenced by alpha. It's not influenced by beta at all. So let's see what beta is in this case, and that's the study here. So here, right, you see type 2 errors committed twice. Run again 3 times. By the way, right, 3 times, right? So not too often, but 1 time. But here, right, alpha is equal to 0.05. Let's make it more restrictive. Let's make alpha to be 0.01. If I make alpha to be 0.01, the anticipation, right, is that there will be less type 1 error committed here. Let's see if that is true. See, now type 1 error is committed way less often in the 10 samples that I look at, right? Because alpha is more restrictive. But if I make alpha to be 0.01 here, what do you think? Type 2 error will be more often or less often? When I make alpha to be smaller, will type 2 error be more often or less often? Oh, sorry, someone's more often. Yes, right. So let's see. Correct. You see, exactly here. But notice, right, here, to calculate the beta exactly, right, you see. So here, this is exactly what I mean by beta is around 40%, right, or whatever. So, but of course, right, these are all simulation. So it's random is one point I want to bring home to you, right, that each time you run it, right, the number of samples that commit type 2 error is random. But overall, right, it looks like to me like about 50%. But if here, right, with this rejection criterion and under mu equals to 1, for example, you can calculate exactly what beta is. Okay, so that's just kind of the simulation about the alpha beta that I want to mention to you. Any question on this simulation? Okay. So now, whoops. All right. So to continue, right? So basically, we were done with 12.2. So 12.1, 12.2, we finished. Next, we'll talk about 12.4, power of a test. And for that, let's kind of map the next several topics that we're going to be talking about. So for that, let's just go back to our example. So recall our example. So we have x1 up to xn, IID, normal, mu1. We have the null hypothesis that mu equals to 0, and the alternative that mu is equal to 1. We consider several rejection regions, C1, x bar bigger than K1, C2, x bar less than or equal to K2, C3, x bar equals to 1, C4, x bar, sorry, S squared, right? We're going to go to K5. And keep in mind that these are only 5 examples we can come up with, right? In theory, you can come up with as many rejection regions as you want. Maybe, depends, it really is up to your imagination that you can come up with some statistic, and then you will reject or accept according to that statistic. So by a rejection region, I mean a structure, right? So for example, notice that this and this use very different statistic. So we say that these are 2 different types of rejection region. This and this has different structure because even though it uses the same statistic, right? One is bigger, one is less, for example. So anyway, right? We pointed out that we showed how C1 is better than C2, C3, and C4, right? And try to recall why, right? I mean, this is the case with the reasoning. And notice that better here is always with reference to alpha and beta, okay? So in other words, that with respect to our goal of fixing alpha and minimizing beta, then C1 among this group seems to be the one that's most appropriate or the best. So now if we go with C1, that what can we do more specifically, right? So now if we pick C1, suppose we pick C1 as our rejection criterion. So by picking C1, I mean I go with this structure, right? Because notice that when I say I pick C1, C1 is not completely specified yet until I know what K1 is, okay? So when I say I pick C1, I just mean that I pick this structure. But so if I pick C1, then now I will need to specify further. So now I can so for a given alpha, I can compute K1, right? So that C1 has size alpha. And that was example 12.2. So to remind you, right, roughly of how the calculation goes, it goes like this. Alpha would be probability that C1 happens under the null. That's the abstract definition. But under a null, everything's completely specified. So we can just plug that into the distribution of X bar. And then you can transform that to a standard normal, which allows you to conclude that this quantity right here would be Z alpha. And then you solve for K1, right? But so after I go with the structure, then I need to still specify the level that will give this structure a size alpha. Is that okay? So that's the next procedure. After that, I can calculate alpha, beta, right? So now when K1 is specified, after K1 is specified, we can calculate beta. Okay, and beta would be probability of the opposite under the alternative. That's again the abstract definition. And again, because now the alternative is completely specified, we can do this and we can plug that in. And now we can plug in, right, this value. Maybe let's just normalize, right? Do the Z transformation. And now plug in. Calculate that. Okay. So this is a routine technical thing that after we decide to go with the structure, we can make the region, right? Make the rejection region more specific and learn everything we need to learn about that rejection region. Is that okay? So the steps are, first decide what the structure of the rejection region is, and then, right, specify the rejection level, what level you want to reject that. And then, of course, after that, you can calculate the beta, alpha, beta. Alpha is given, right? Alpha is given. Beta is what you want to figure out because no one will give you beta according to the testing convention that we always follow, right? That actually is the only testing convention that everyone is using. I'm not aware of anyone else not using this convention. Is this okay? Any question on this? So you want to be able to apply this procedure to any other type of sample, right, with any other population and any type of other, right, rejection region that you may be given. So, right, given a rejection region, you should be able to perform this task. Is that okay? Now, absolutely, because if you don't specify K, then this rejection region is not completely specified, right? It's completely abstract. Because when you reject, right? I mean, your boss tells you to come up with a rejection region. You say, boss, you reject when the sample average is bigger than K. And your boss is like, okay, so what? What's K? Yes, I mean, even in conversation, without specifying K, it doesn't make sense for us yet. Is that okay? Mm-hmm. Any other question? So now, these are the so-called easy question, easy in calculation that you guys can carry out for yourself. The harder question, right, are the followings. How to come up with a rejection region? And two, how to know if our rejection region is the best. Okay. So let me explain. Flavor-wise, this is very much, you mean here, Madhav? Okay, last step. All right, so okay, right. So here, apply definition of beta. Plug in the alternative, plug in mu, do the Z transformation, plug in the value of K1 that I got from the alpha specification. How did I get the test stat Z alpha? You use the wrong word. Oh, you mean how do I get K1? Yeah, by the way, right? Test stat here would be X bar. Z alpha is just something that comes out from the level alpha. Okay, so Z alpha is not a test stat. But that level, I mean, I guess according to what Jen Ling was asking, that comes from the specification of alpha. Are we okay here? Yeah. All right, so flavor-wise, all right, this is very much similar to the method of moments. I mean, I'm not saying that this is method moments, but the type of question we're asking is very much similar to when we were studying estimators. So remember, right, when we study estimators, first of all, we just study any estimators that people can give you, right? If someone gives you some estimators, then you can study the sampling distribution, expectation, variance, etc. Then there's a question of how do you come up with an estimator by yourself? And then you're given the methods of MLE and method of moments, right? So same thing here. This question is, all right, I mean, you can see that these are some rejection region that I came up with by my imagination, more or less. Okay, and you see, it's exactly because it's my imagination. Some of them don't make sense. So that's why we went through some, time analyzing how they make sense and how they don't make sense. But ultimately, there's no routine, right? There's no methodology of how do we come up with this. So that's the first question. So let me give you a sneak peek. This question is answered. There's no right or there's no right or wrong answer to this, right? The how to, it's just different methods. So the answer for this, there are several answers. One answer is called likelihood ratio test, which is a big deal because likelihood ratio test, you will see it in many contexts in advanced stat and in machine learning, that kind of thing. But this is not the only answer possible, because as you guys are already familiar, you know of the t-test, z-test, the chi-square test, etc. Right? So I'll just call them routine traditional tests. Right? The t-test, the chi-square test, the f-test, that kind of thing. Now, if you don't know them, don't worry. Okay, I think that some of you might have heard of this before. But this routine test actually is not really the answer. These routine tests, as I will try to show you, actually have connections and are motivated by the likelihood ratio test in some way. So the how to, when I ask this, I want to have a methodology, a method. So the only method or the only kind of like universal method I am aware of is the likelihood ratio test. All the other ones are sort of like intuition-based kind of approach. So anyway, right, but I will list them here. We will tackle this in, so likelihood ratio test is going to be 12.5, I believe. Let me see if that's true. No, 12.6, I think. And routine test will be chapter 13. Okay, I'll just do that. Anyway, today we'll focus on the second question: how to know if our rejection region is the best. The flavor-wise, this is similar to asking how do we know if an estimator is the best. And at that point, right, remember I said, well, it depends on your comparing, right, your criterion. So if you use mean square error as the criterion for comparing estimators, then it's hard to tell. But if you restrict yourself to the class of unbiased estimators, then Cramer-Rao lower bound is the way you can tell, right? So Cramer-Rao lower bound gives you a very beautiful way to tell if some estimators have achieved minimum variance among the unbiased class. So the UMVE, right, you can come up with, you can say that this estimator it achieves the Cramer-Rao bound, so it's the UMVE. So same thing here. The flavor is this, right, that in this rejection region, I have argued that C1 is better than these. On the other hand, how do I know that C1 is the best? Meaning, because my imagination is limited or because my time is limited, I can compare C1 with C4 if you give me C1, C4. But among all the possibilities that one can come up with, how do we know that this is the best? That any other structure you can come up with would not beat this, okay? In terms of like type 1 and type 2 error, how do we know that? So that's a really important question, and I hope you appreciate this is a really hard question to answer, because you must be able to somehow classify, right, all types of rejection region possible, okay? And the structure, right, is, like I said, is really as rich as your imagination. So how do we do this? The answer to this is exactly through the Neyman-Pearson lemma, which is 12.4, which is what we're going to get to today. Okay, so Neyman-Pearson lemma tells us when we can know that a critical region that we come up with is the best structure there can be. All right. So these are the two questions these are the plan that we will be doing for the next couple lectures or so. Any question on this? All right. So now focusing on 2, let us introduce one more concept, one more terminology. Is really not something big, but we want to define the power of a test. And power, I don't think there's a notation for it, but power basically is 1 minus beta. Okay, so I don't know why, but conventionally people just come up with this concept and discuss it. As you can see, discussing power, discussing beta is exactly as discussing power. But so the reason is this, that people like to say, right? So before, we want to fix alpha and minimize beta, right? So now with the concept of power, what you want is you want to fix alpha and maximize power. That's it. And so that's why you will hear that this test has more power than the other test. Basically, it has smaller beta, right? When you compare 2 tests. When one test has higher power, that means it has lower beta. So then the goal, right? Then we can rephrase our goal is to come up with a critical region of size alpha, because alpha is given, right? With the highest beta possible. Sorry, highest power possible. Okay, that's it. So let me show you a curve from the textbook. Let's see where we are here. 342. Oh, right here, right? Right here. Yeah. Actually, you see, this is from last time I taught the course. I still have this. So let's see. So what are these curves? And this is really the only thing I want to say about this section. This is from section 12.5. So after you define, right, beta, so maybe let me say this, right? So maybe let me backtrack. So you can define a power function of a test. And so, by the way, right, let me clarify what a test means here. So the context is that you have the null and you have the alternative. These are fixed. All right, these are fixed in this discussion, meaning we will never change the null and the alternative. So when we compare different tests like this, so this is the power function of one test, this is power function of another test, this is the power function of the third test, okay? So these are three tests that they are discussing in this graph. When they say that, when they consider a test, that means that this is different critical regions they come up with. All right, so a test here is basically the same as a critical region. Are we okay? So in this discussion, the null and the alternative are fixed. So when we say a test, we don't mean like this is a different hypothesis. No, the hypotheses are fixed. We want to come up with critical regions, and we call that a test. And we say this is a power function of this test, meaning this critical region. So the flavor is exactly the same as the example we discussed last time, right? Comparing different critical regions. So power function of a test is basically just the probability of that critical region given theta. So it's a function of theta. All right. The power function of a test is a function of the true parameter theta. And it's the probability that you are in the critical region for a given value of theta. And that's why you see theta is graphed here. Oh, by the way, right, I think they call it pi. So let me call it pi. Are you okay on this? On this definition of power function of a test. For different values of theta, right, we have different probabilities. But of course, because it's probability, it goes from 0 to 1. And here you graph for different possible value of theta, how this comes out. Okay. So what do we want with this power function? What is some desirable? Okay, maybe let me ask you this, right? See if you understand this concept. What does a good power function look like? Can you tell me? If this is our power function, and suppose you can graph it, right? Notice that this requires you, so basically you must first come up with a C, right, with a critical region. So these are three different tests with three different critical regions. And then you have to go and calculate, right, these probabilities for different values theta, then you go and plot them. Anyway, right, this work has been done for you, or this is just hypothetical. Now, suppose then you take a look at these. What does a good power function look like? Or maybe that's a hard question, right? Let's zoom into this first. Notice that these three curves all cross at the same point, theta naught. What do you think this is? What do you think this is? Theta naught here, right, must be the null hypothesis. Okay. So theta naught here must be the null hypothesis. So this value right here, roughly 0.2, what do you think this is? Exactly, that's alpha. Why? Right here. Because, right, if this is the norm, then this is type 1 error. So, yep, very good. So do you see why all these three curves, even though they are with different tests, they all cross at the same point at this point? Why is that the case? Why do these three curves all cross at the same point? Yep, all tests must have size alpha, right? Remember our convention. Our convention is the test has to have size alpha, isn't it? So all tests have size alpha. Is that okay? That's why all these curves cross at alpha. Any question on this? Okay. So maybe, right, it's still a bit of a jump, but now can you tell me what does a good power function look like? So by the way, right, where's theta 1? Oh, where's the alternative here? Where's the alternative? Exactly, right? The alternative, I haven't shown them yet. Exactly, it could be anywhere. So now let's suppose that this is the alternative. Okay. Then maybe let me ask like even kind of maybe a easier question. This is A, B, and C. If theta 1 is the alternative, which one is the best test? Correct. A is the best test because it has highest power. Right? So what's type 2 error for this test, for example? So right, for example, let's say here roughly is 0.9. What's type 2 error for test A? 0.1 exactly, right? So you understand that this is, so right here is type 1 error, but out here, right, it's going to be 1 minus type 2 error. Very good. Exactly. So, all right, with that said, can you tell me, right, what does a good power function look like now? Almost, but be careful to separate highest and steepest, okay? Highest is about the value, steep is about the derivative. I think you mean highest. I don't think steepness has much to do with this here. Highest, but high is not always there. That's fine, right? High is not always the point because so you have to write again, even though we understand that alpha is taken for granted. So yeah, so it will be this, right? Oh, exactly, right? Because for example, suppose that this is theta 1. Then which one is the best? Exactly, right? So a good power function would be something like this. And this is vague, but I hope it captures this. It's going to be low over the null. It's going to be high over the alternative. What are you trying to say, Chanlin? You're trying to describe the curve? Uh, I would say the power function curve doesn't have to be a quadratic function or something like that, right? In general, actually, it's going to be quite tough to graph this, and actually we don't know the structure of it so much. This could come up from a come from a real test, but as far as I'm concerned, right, this is just like hypothetical curves to give you understanding on what a power function looks like or what a desirable test looks like, right? So hypothetically, you can compare this, but do remember that if you want to carry this out, even for a simple example, it will be super painful. Just think about it. Just think about, because here you have to map it for each theta and etc. All right, it's not that easy. There are many things unrealistic on these curves. Yeah, but we'll, right, just demonstrating the concept. But I hope everyone got this message, right? Low over the null and high over the alternative. Is that okay? That's what a good power function looks like. And really, right, most power functions should be bundled around the null because, like Jianlang was saying, right, alpha is controlled, fixed alpha, right? So most of the times you kind of take the null for granted, but still, there's something you have to say, because if it doesn't meet the size criterion, then we don't use it to begin with, right? Our test must have size alpha. But the real play, right, is over the alternative. By the way, for example, now, so what kind of hypothesis have I've been drawing here? This picture. What kind of hypothesis? Exactly, right? I've been drawing simple hypothesis. Do I have to? No. I can do this. Suppose this is my H1, right? So you understand, this whole region is my H1. Is it okay? So now this is going to be composite. Now, given that this whole region is H1, what is the best test in this case? If I change this to my H1, what is the best test in this case? It's not a trick question. It's still A, right? Because A is still highest over this region, right? So I just draw this picture to demonstrate to you that you can analyze the composite hypothesis. But for this one, it's still A. You know why? Because these curves are very simple. Exactly, right? That's exactly where things get interesting, because what if the curve does something like this? Then what is the answer? The answer is there's not necessarily a comparison between these two. Is it okay? So these pictures tries to, you know, give you some concept, but yes, right, do keep in mind that reality is much richer than this is. Also, right, the null here, because of this picture, I can't change this picture so much without destroying certain things here. But the null doesn't have to be simple either, right? The null can be composite. But if the null is composite, the restriction must be a little bit different than this. Are we okay? So the curves don't have to be always obey the same order like this. All right. And this, by the way, right? So what does this simple thought experiment demonstrate? That when you have a simple hypothesis, right, no an alternative, then the question of best critical region, or best test, can be decided in simple hypothesis. Okay. But if the hypothesis is composite, you may or may not be able to decide it. It really depends on how the power function is structured. Are we okay? So actually here, I must say that best critical region can always be decided under simple hypothesis because you're just comparing 2 points. But not necessarily so, right? I won't write this down, but best, the question, right? Remember, we were still after the word, the question of the best test, the best critical region. If the hypothesis is composite, sometimes that question cannot be answered because, you know, the curve can do something like that over your region. Are we okay here? All right, so that's all I want to say, right? So this picture is quite interesting. I mean, that's all you need to get out of from section 12.5. Okay, the concept of a power function, which really is what we have been doing so far in a way, just kind of codified in a more visual way. And it also highlights how you can really, right, select a single theta out from the rejection region or whatever from the hypothesis, from the hypothesis, and then calculate the probabilities, right? So I think that message is quite good because, like I said before, right, unless the hypotheses are simple, this question may or may not be computable, okay? But this can always be computable. So that's exactly what I was discussing as well. Anyway, the conclusion right here will lead us to Neyman-Pearson lemma. In other words, Neyman-Pearson will tell you, so Neyman-Pearson lemma will tell you what test is the most powerful test, but Neyman-Pearson only, the statement of Neyman-Pearson is stated for simple hypothesis. Okay, and if you wonder why Neyman-Pearson is stated by simple hypothesis, is exactly because of this picture. So in case you get confused later on when we discuss Neyman-Pearson about this kind of setup, this is the reason. Any question? All right, so now let's go back to, so now, right, we are done with 12.5. So 12.5, right, power function of a test. We're good. So now 12.4, Neyman-Pearson lemma. Okay. So first, let me tell you how it's used, because when first people see Neyman-Pearson, they are quite confused about the statements, etc. So let me say several things about the Neyman-Pearson, and then we'll maybe not today, the next time we'll prove it, or state and prove it. Okay, we'll state today too, but so let me first tell you what is it, how it's used. Its use, right, is to tell us. So, all right, sorry, maybe first setup. The setup of Neyman-Pearson is always about simple hypothesis. In other words, something like this. Okay, Neyman-Pearson is about simple hypothesis. Again, you ask why? It's because it tries to do most powerful test, and most powerful test may not be decided, right, under composite. Okay, use is going to be used is to tell us when, right, a test, and obviously a test here means a critical region is the most powerful. Of course, right, most powerful what? Of size alpha. Without some restriction, you can never, right, compare. So among the critical region of size alpha, the one that satisfies Neyman-Pearson criterion is the best, meaning the most powerful. All right. So is again, the flavor is all very much like the UMV, right? Among the unbiased estimator, the one that meets Camara lower bound is the lowest variance. So among the critical region of size alpha, the one that satisfies the Neyman-Pearson criterion will be the one that's most powerful. Finally, let me tell you the connection and where it comes from. The connection is with likelihood ratio test, and that's the big deal. Because like I said, the likelihood ratio test is the only universal concept that I'm aware of for hypothesis testing, okay? So these 3 points, the broad strokes of Neyman-Pearson that you want to keep in mind, okay, when you study it. The exact statement will be like this, which will be a little bit confusing when you first see it, but it's quite okay, actually. So first statement, the statement is this, right? So given a critical region C, right? Notice, right, so in Neyman-Pearson, we assume that the hypothesis are already given and fixed, all right? If there is a K, a value K, small k, all right? So that the likelihood function under the norm divided by the likelihood function under the alternative is less than or equal to k in C, and the opposite happen. Sorry, this is a vector. Bigger than k in C complement, then C is the most powerful. Of course, right, of size alpha, whatever, but we already say it. All right. I guess this is bigger than equal to, doesn't matter. So let that sink in a little bit. What's going on here, right? So there are several things. Forget about, right, the whole statement yet. But first of all, it requires you to have already a critical region. Then, right, it asks you to construct a likelihood function of your sample, of course, right? This is why the vector x is here. The likelihood function will be different, right, under whether the null is true or the alternative is true. Why? Because the likelihood function is a function of the parameter. If the parameter change, then the likelihood function change, right? So these are two different functions, so you can form a ratio. This little k here is a mysterious k, all right? This little k is usually found after the fact, meaning after you form this, then you say there's such a k. And this k usually is not found explicitly, all right? So I'll make a remark here and I'll do an example. I'll show you. K is usually not found, meaning you don't need to, not necessarily. Explicitly. I'll tell you this because students, right, when they see these things, when they say when they see that there is a k or whatever, they feel like they must exhibit what k is, right, to satisfy this result. Abstract math, right? When you say there is something, somehow it's beautiful that you don't even have to say what it is, but you say there is such a thing. So, right, and I'll show you. So anyway, right, one more thing, and then I will kind of do an example. What's the intuition here, by the way, right? What is the intuition here, by the way? So the intuition here is this, that C is when you reject. C is when you reject, right? So if you were to reject, then the likelihood, right? Remember, what's likelihood function? Likelihood function tells us how likely it is that we observe this sample. Okay, you have a sample, right, given right in front of your eyes. Likelihood function tells you how likely it is that you observe this particular sample. But if you were in the rejection region, meaning if you truly reject, then the likelihood under the null should be smaller than the likelihood under the alternative. Agree? Because you are trying to reject. So the likelihood under null should be smaller than the likelihood under the alternative. On the other hand, if you try to accept, then the likelihood under the null should be higher than the likelihood under the alternative. Okay. Now the actual math turns out to be a little bit more sophisticated than this, but the intuition is along that line. And actually, again, that's as crude as it is the intuition behind the likelihood ratio test. You don't know which hypothesis you want to go with. Guess what? Form the likelihood ratio under these two hypotheses, right? Try to actually, I don't know how to say this. It sounds more fancy than it is in math language. In real life, it's very simple, right? We do this all the time. Like, for example, you don't know it's rain or shine, right? So these are two hypotheses, rain or shine. You see someone walk into your classroom with a wet umbrella. Guess what? You immediately say it must be raining outside. Why? Because under the null, under the hypothesis that things are it's sunshine out there, it's not likely that a person is going to walk in with a wet umbrella, right? I mean, the wet umbrella can come up from different reasons, but right. So basically, you want to know if these two hypotheses, which one is right, which one is wrong. You have your sample, you have your evidence. You think of how likely this evidence happens under null, how likely this evidence happens in the alternative. You weight your evidence. If it's small, you reject. If it's the other way, you accept. The person have a wet umbrella is the likelihood function, right? Actually, the person with the umbrella is likelihood function. It being wet is the likelihood function under the alternative. I mean, sorry, how to say this, right? Is the outcome of likelihood function, right? It being wet under the null, which is sunshine, is very low, right? You understand what I'm trying to say? So the person having a wet umbrella is the likelihood function. Or the state of the umbrella is a likelihood function, right? It's wet under the alternative and it's dry under the null, isn't it? Does that make sense? Yeah. So again, maybe my example doesn't really, get I don't know, pigeonholed into this example. What I'm saying is you always weight examples. Sorry, you weight evidence, right? We always weight evidence under hypothesis anyway, right? So I don't want you to get like super scared by this statement. It's a very natural statement. It's just weighing the evidence under the null and the alternative. If the weight favor the rejection, then we reject. If the weight sample favor the acceptance, then we accept. That's it. Except that Neyman Pearson says somehow if the split is perfect, then you have a very good rejection region. That's it. Is that okay? All right. So now let's look at an example, right? Let's look at the example we have. And show you how, because pay attention, this math here may be a little bit tricky if you haven't, you saw it the first time. So let's look at x1 up to xn, IID, normal, mu1, okay? I will do it abstractly. Let's say mu, the norm is mu equals to mu naught. The alternative, mu equals to mu1, with the assumption that mu1 is bigger than mu naught. All right, this is my setup. My claim is that the rejection region is the most powerful. or maybe it's a most powerful, right? The word the and here is a little bit kind of whatever, because who knows, but it's the most powerful of some size. So in other words, this kind of goes back to the question I was discussing before, that among these guys, right, I can clearly see that C1 is better than C1, C2, C3, C4. But by C1 itself, how do I know it's the best? Because there could be C6 up to C10 that I haven't considered. Now, right, notice this is 1 bigger than 0. Now, Neyman Pearson would say that by Neyman Pearson, I can now confidently say that, yes, that's the best. All right. So the proof, or, you as students will be asked to come up with this proof. So the problem will say something like, prove this is the most powerful by Neyman Pearson, using Neyman Pearson. All right. So that's the question, right? So question, right? Prove this claim by Neyman Pearson, using Neyman Pearson. Okay. So how would you answer this question? You would do it by steps. First of all, you would try to form the likelihood ratio. So the word likelihood ratio is going to be used quite often from now on. So I will just do this, okay? Likelihood ratio. What is the likelihood ratio? Well, the likelihood ratio, right, will be likelihood function, right? Here given mu, right, will be the product of 1 over square root of 2 pi e to the minus x minus mu square over 2. Yes, because these are normal with mean mu and variance 1. All right, so when I try to form the ratio, right, the ratio will be L under mu 0 divided by L under mu 1. Well, I hope you see, right? First of all, this constant goes away. You will get, oops. Oh, sorry, this is xi, right? You will get this, e to the minus the sum of xi minus mu 1 square over 2 minus the sum of xi minus mu 0 square over 2. Sorry, the other way, isn't it? It's important here. Is that okay? So you will need to do some algebra to kind of clean up the likelihood ratio a little bit. And this is not quite cleaned up yet, by the way, right? This is not quite cleaned up yet, by the way. But any question here about this structure of the likelihood ratio? Okay. And oh, maybe I should say several more things. Don't confuse this big K with the small k in Neyman Pearson, all right? This is the K of the likelihood ratio. This is the big K about rejection region. This is capital K. They're not the same, all right? They are related, but they're not the same. But anyway, right, our goal is to kind of somehow say that this is bigger than K or less than K, etc. So notice that the exponential function doesn't do anything because the exponential is an increasing function. All right. So the real player is this right here. All right. So I will focus on working on this. How do I do that? Well, I mean, I just look at this, right? And I even forget the over 2. Now, again, right, these steps are why I think students will find Neyman Pearson a little bit challenging. You just have to kind of remember the goal. Your goal is to show something is bigger than some number. So you kind of ignore anything that's sort of like increasing or decreasing, and you just focus on the real player, which is the sample. All right. And so what is this? Well, let me just expand them. All right. Yes. And so notice these cancel, right? And the simplification goes to minus 2xi, right? There's a sum, mu naught minus mu 1, and then plus mu naught square minus mu 1 square. Question in any of these steps? All right, so plug that in, I get my likelihood ratio will be exponential of, right? This minus and this minus cancel. So I get, roughly speaking, 2 mu naught minus mu 1 sum of xi. Oh, the division by 2 also cancel, right? Like this. With some constant outside. What constants? These constants factor into the E. All right. I think some of you or many of you may have been confused by this moment, which is fine. Can you tell me why? Eventually, I want to come up with this structure. What is it? Or why is it? What is it that I'm trying to do here? What's the big threat? Big theme here? What are we trying to do? So it's hard, right? So this is where like we need to keep Neyman Pearson in mind. Neyman Pearson wants you to show that the likelihood ratio, this guy, is less than k in C and bigger than k in C bar. What's our C? This is our C. So maybe before the step, right, I need to show you the goal, because if you don't keep the goal in mind, maybe you will be lost. Goal is to show that the likelihood ratio is less than or equal to k. What's in C for us? When x bar is bigger than to k, and this when is that okay? This is Neyman Pearson. Neyman Pearson tells you exactly this. In the abstract, in the concrete case of our example, this is what Neyman Pearson tells you. Where, of course, what is this? This expression right here. How do I get it? By all this work. Any question here? All right, I know we're right at the end of the class, but let me ask you this, right? I want to finish this. Do you see that this is true, given this? I claim that I'm done. This is it. But of course, this is one of the moments that also mystify the students. I'm done. I've got it. Do you see why? I'm done because this is going to be exponential of one more step, n mu naught minus mu 1 times x bar. And what's the relation between mu naught and mu 1? Mu 1 is bigger than mu naught. So this is going to be a negative number. So therefore, my likelihood ratio is a decreasing function of x bar. That's the point. Because mu naught minus mu 1 is negative. And because it's a decreasing function of x bar, that's what happens. That's it. That's what decreasing function does. Right? Because let me draw you, right? So here, suppose this is x bar. This is my likelihood ratio. You say it's a decreasing function, right? I don't care how it looks. Suppose it looks like this. Then, right, notice this is exactly my big K. Suppose this is my small k. You see that when x bar is bigger than big K, my likelihood function is less than small k. And when x bar is less than k, my likelihood function is bigger than big K. So this is just a picture to tell you, to give you the visual help. But the point is, this and this actually says the same thing. And we're done. All right. So again, a lot of abstract kind of combinations here, okay? But the flavor of Neyman-Pearson proof is like this, and we'll do more examples next time. All right, so sorry for keeping you over. We're done today. If you have questions, I'll answer. If not, you know, don't forget the test is on Friday. Thank you. You too. Wrong question. Even though, yes, what you observe is very good, but it's not about the best big K. Because remember, what's the story with big K? There's no best or worse. What's a big K? Big K is specified by alpha, right? So that's it. Yeah, you did. Big K is specified by alpha. So Neyman-Pearson doesn't care what size you have. It cares about the structure. Exactly, right? And you see, this doesn't play any role because that's why I don't care for it, right? The whole dependence is from likelihood ratio on the sample. And that's always the message, right? The likelihood ratio is a function of a statistic or is a function of the sample. And that's why you can directly relate this. It's only the sample that matters. The constant are universal, they don't change. So why do we care about them? Is that okay? Any other clarification?
Can you go over the differences between size of a test, alpha, and critical region? Like just in terms of terminology, since alpha is equal to the size of the test, but
Yep.
when they're asking for like what is the critical region of a test, it doesn't necessarily mean alpha, right?
No, so it's like this, right? I mean, suppose you have a random variable x. You know, so the saying x bigger than 5 is an event. Saying probability x bigger than 5 is a number, right? Between 0 and 1. Right? So X is our test stat. This is a critical region. This is alpha. So they're different objects of they're all related, but they're different objects of different things, right? So this is our random variable test stat. Critical region, by the way, another way to think of it is critical region is just telling you the event that when it happens, you reject. That's it, right? Critical region is an event, right? X bar bigger than K is an event. How likely does that event happen? Well, how likely does that event happen under the norm? That's alpha. So the only sophistication is we add the hypothesis on it, right? Does that make sense or no?
Yeah, that makes sense. I think, oh wait, sorry, continue.
So yeah, just one more thing. Maybe the thing that confuses you is this, right? Suppose this is 0.1. Is this the only event of probability 0.1 related to X, for example?
No.
Right, so exactly, you could have many other events, for example, X less than -6, for example. It could be that this is also 0.1. So alpha, right, is a very generic number. It's just a level that we want our probability to have. But it's selecting that event, selecting a meaningful event, right, for whatever reason it is what we're after. So that's why, right, we want to select a critical region of size alpha. Does that help?
Okay. Okay. So you want to select a critical region of size alpha. Okay.
Alpha is always given, right? So again, the story is like this. You want a level of type 1 error. You have to sample right in front of you, right? I mean, I don't know, like again, think of like the jury example, right? You want to conclude this person is innocent or guilty. You have all your evidence in front of you. What criterion are you using to decide if this person is guilty or not? Now, a terrible example would be someone would roll a die, and if it's even, the person's guilty. So what is that? That's 50-50 chance, right? Another one would flip a coin, again, 50-50. A third person would weigh the evidence, the real whatever criminal evidence. But just because that person weighing the evidence, does that mean that person doesn't make a mistake? No, right? But these are three different critical regions. Do you see that?
Yeah. So in order to compute like an actual value of a critical region, you need to set alpha or else you can't find it, right?
Opposite.
Oh,
So, okay. No. Okay. So, okay. I see what you're asking now. Fine. So the story actually is something like this, right? Right here. So conventionally, right, you want to settle with a structure of the critical region. In other words, right, you want to see what test that you want to use and what level. Again, go back to like a criminal justice example, right? Maybe you want to have the evidence that this person is very abusive. I don't know. Maybe that's your criterion. And then maybe your level is that he must have like hit 10 people to say that he's guilty. But another person may set a level lower, right? 7. Does that make sense? But first you must settle on a type of evidence you want or the type of stat you want. And then, right, you must settle on the structure.
Yeah, that makes sense. Sorry, I was just it was just a homework question that I was like a little confused about because it said like find the critical value for a given level of alpha. But I guess it makes sense when you're creating
critical value, I guess, would be the K, right? Is that what they're asking? Which homework question you're talking about?
It was number 7, 12.7, but I figured it out. But I was just like a little confused when it said what is the size of a critical region.
Oh, you know what? Let me see here. What is the size? Because they already give you K.
Yeah.
Because
okay,
they give you K to be mu naught plus 1. Yes?
Yeah.
So I see why you're confused, because it kind of goes opposite of the spirit, right? And I usually said, right?
Yeah.
Because usually I say that alpha is given and you find K. Yeah, 7 is exactly the opposite. Somehow they give you K1 because they say that now C1 will be X bar bigger and equal to mu naught plus 1. That's what they give.
Okay.
So
Yeah.
abstractly, there's no reason why you cannot do one way or another. But conventionally, right, I feel this is weird. Why would you do this? I mean, you could do this and then just in the dark and try to see what's the alpha and then see if you like it or not, right? But what I was lecturing and what I was telling you is what typically happens in practice, because you don't want to play around with too many different levels, right? That's stupid. You want to set an alpha first and then find K. Does that make sense?
Yeah, that makes sense. Okay, so the homework question just goes against the convention.
Opposite. I mean, again, right? There's no reason why they cannot ask a question, but it feels like they're just playing around with the math rather than going to a flavor of stat. Does that make sense?
Okay, yeah, that makes sense. Okay, great. Thank you.
Sure.
Professor?
Yeah.
I had a couple of questions about confidence intervals, but I know we're past class hour now, so I thought I'd save it for office hours. Will you be having office hours this Thursday?
Yeah, well, you can ask now if you want. It's up to you.
I mean, there are quite a few actually, so I'll just wait for office hours and I'll ask you then.
Okay, that's fine. Yeah, okay. Then I'll see you.
Thanks so much, Professor.
Sure. All right. Take care.